We will now look at two relaxed memory models in more detail and their motivation. So the most important improvement over sequential consistency is weak ordering, and it was invented by Michel Dubois at the University of Southern California in Los Angeles. And the key idea for why it is useful is the following. Consider a critical section, and a thread first takes a mutex before entering it, and then modifies some shared data, and then unlocks the mutex. So with sequential consistency, we would still use the mutex so that there are no data races. I mean, for instance, if we update some data structure, it should clearly not be done concurrently by different threads that would corrupt it. So we still need mutexes also for sequential consistency, of course. But when we now have mutexes, why should we wait for each individual store instead of not waiting just at the end of the critical section? With the relaxed memory model, we assume that there are no data races, meaning that no other thread is reading what is being modified in the critical section. And that is how it should be. So sequential consistency, in a sense, adds artificial constraints on the execution, which can be avoided. Okay, so if we now have weak ordering, we can issue lots of writes, and they will be executing in a pipeline. And when the CPU reaches the mutex unlock, then it does this sync instruction. Also at the beginning of the critical section by the lock instruction. I mean lock operation. Okay, so this does not always improve the performance significantly, because it may be the case that the cache already owned all or most of the data that is being modified. Then it has no performance effect. But otherwise, sometimes it can improve the performance by 10 to 20%, for instance, according to measurements. Okay, so release consistency, it is an improvement of weak ordering, and it was invented by Kourosh Garashullo at Stanford University for the Stanford Dash project. And instead of having only one sync operation, there is one operation at a lock and another at an unlock. And the acquirer orders all memory accesses after the acquire, meaning that they cannot be moved to before the acquire. And the release orders all previous memory accesses, meaning that they cannot be moved to after. So what we can see is that we have a pair of acquire and release, and between them in the program there are lots of shared memory accesses. And these data accesses between the acquire and the release, they can be reordered in any way, but none of them can move either before nor after the release. They are locked in to this critical section. Okay, so if we compare weak ordering with release consistency and see what they permit. First, when we write A and followed by B, we mean that we may execute B before A. Okay, so weak ordering, it permits data operations, I mean reads and writes to be reordered, but not sync and not sync and data. And not data and sync either. Okay, and release consistency, it permits this same data reordering, and this is the most important part, as we can expect. Most of the memory accesses are not sync instructions, but they are instead reads and writes to share data. And a data access before the acquire, it can move into after the acquire, and the data access after the release is allowed to move into before the release, and a release is allowed to be reordered with an acquire. But these two are what I explained, that the data accesses are locked in, so to speak, between a pair of acquire and release. Okay? There is not very big difference in performance, but of course, if we count clock cycles, which we perhaps like to do, then release consistency is preferable. So how can we, well, this is a preview of the next lecture, but how can we control the memory consistency model used in C and C++? With atomic variables, we can specify the memory order. So there are symbolic constants that say, for instance, memory order relaxed. And if we load an atomic variable, so we take the address of A and read it into X, then when we have this explicit, it means that we can specify the memory order. And if we use this without the explicit, it is by default memory order sequential consistency. But more about that in the next lecture.